Hey everyone, Mr. Weiser. We're going to be going over Module 3, Lesson 1. This is going to be in your new booklet for Quarter 2. So let's begin. In your textbook, it'll be found in sections 2.1 and 2.2. We're going to be talking about two things. We're going to break this video up into two parts. So this first part is going to be talking about describing position in a distribution. So let's first talk about a couple of test scores. Let's say I got a 40. Robert got a 40 out of 50. 80%, not too bad. We look at this distribution. We want to see where does that 40 compare to the others. So what I'm looking at is with that mean of 35.44, clearly Robert is a little bit above the mean, but how much above the mean? We look at our standard deviation at 8.77, and we can answer a few questions related to all that information here. So the first thing we want to do is think about how his score compared to the rest of the class and how many standard deviations above or below the mean he was. So let's talk about percentile first. With percentile, what you want to do is you want to look at the percentage of people in a distribution that are less than or equal to your value. So if you're at the 50th percentile, you're right in the middle. You're exactly in the middle of the average. So if you're at the 80th percentile, that doesn't mean you got an 80% on something. That just means that you're 80%, 80% of the students are at or below where you scored. So how that works for Robert in this case is we look at where 40 is, we count out all the dots over here, take a little counting exercise and see what you get. You should get 18 dots. So 18 out of the 70, out of the 25 dots that were originally there. And so you can divide those two numbers. And 18 divided by 25 is 0.72. That translates to the 72nd percentile. So Robert's score of 40 is actually at the 72nd percentile according to that class. We can also calculate something called a z-score, which is a standardized score, and it tells you how many standard deviations above or below the mean you are. So in this case, the formula is going to be the same. It's you take the value, subtract the mean, and then divide that number by the standard deviation. In the case of Robert, again, we can take that 40, that's his value. We can subtract the 35.44, and you get 4.56. And then if you take that and divide by 8.77, you'll get a z-score of roughly 0.52. The interpretation of that is Robert's score was 0.52 standard deviations above the mean. All right, let's begin the example. Now that you've seen how to work that out, let's look at example one. So this is the Flint water stuff that we studied at the beginning of the unit, not the unit, the course. And once again, here's the dot plot for those summary statistics. There are 71 samples and a lot of outliers in this case here. But let's calculate the percentile for the water sample for a lead level of 9 parts per billion. So what we want to do is we want to look at where 9 is. And we're going to have to count all the numbers 9 or below. Now that's going to be kind of hard to count, so you may need to pause the video and try that on your own. All right, I'm going to reveal what I counted. 3, 2, 1. You get 59 numbers. So what we do is we take 59 and we divide by 71 to get 0.83, which is the 83rd percentile. The interpretation is 83% of the homes had lead levels at or below 9 parts per billion. Part B, US EPA regulations require action to be taken if the 90th percentile of lead levels exceeds 15 parts per billion. Based on these data, should action have been taken? Well, let's look at where 15 parts per billion are. Clearly, there are several numbers that are above there, but is the 90th percentile above the 15 parts per billion? So we're going to work backwards to get this value. We know that it should be equal to 0.90 since it's the 90th percentile. We know there are 71 data points. We just have to solve the equation. What is the x value? What are we looking for? Now, that x value doesn't tell you the parts per billion, that tells you the position. So x divided by 71, we're going to multiply by 71, and we're going to get 63.9. That's not 63.9 parts per billion. That's not over here. There's no point over here. It's the 64th position. So what we want to do is we want to figure out where the 64th position is. So what I would suggest doing, since there are only 71 positions, is count backwards. 71, this would be 70, 69, 68, 67, 66, 65, 64, and that looks like it's going to be right there. So it does appear to be higher than that 15 parts per billion. So we're going to go ahead and say that, yeah, that water is pretty unsafe. So since the 64th position is above 15 parts per billion, action should have been taken in this case. Part C, calculate and interpret the Z-score for the water sample for Leanne Walters' home, which had a lead level of 104 parts per billion. So hers is all the way over here at the outlier at 104. That's that 71st position. So what is the Z-score in this case? Well, it's going to be value minus mean divided by standard deviation. And you have the mean and the standard deviation and the value at 104. So you'll just plug those into the formula, and then we'll make that interpretation. See what you get. All right, here's the solution in 3, 2, 1. So value minus mean divided by standard deviation will give you 104 minus 7.31. Subtract those, divide by 14.347, and you'll get a Z-score of 6.74. What that means is 6.74 standard deviations above the mean, above the average. So Leanne's home had a lead level 6.74 standard deviations above the mean. That is the interpretation. All right, letter D. The lead level in a different Flint Homes water sample had a standardized score of negative 0.37. Again, remember that's Z-score when you see standardized. Find the lead level in that home's water sample. So this is, again, another working backwards. Again, this is Z-score. So remember the Z-score formula is value minus mean divided by standard deviation. But in this case here, we have the Z-score. So what we have to do is we have to plug in the mean, we have to plug in the standard deviation, we have to solve for the value. So a little bit of equation solving will get you the answer here. So see if you can set that up and solve it. All right. So hopefully you multiplied the 14.347 by this number here, but then you added that 7.31 to both sides. You're going to get a value of 1.97. So what that means is 1.97. Now we don't really have a 1.97, so that's about 2, would be a Z-score of negative 0.37. So it's about 2 parts per billion. The loud level for this home is 2 parts per billion. It's going to be right here in this column here where all these 2's are. There's a lot of 2's. So that's going to be a little bit below the average. Now let's do some comparisons. Jordan was 55 inches tall at age 9. The distribution of height for 9-year-old girls has a mean of 52.5 inches and a standard deviation of 2.5 inches. Zane, on the other hand, was 58 inches tall at age 11. The distribution of height for 11-year-old boys has a mean of 56.5 inches and a standard deviation of 3.0 inches. Who is taller to other children of their sex and age, Zane or Jordan or Zane? Justify your answer. Clearly, we know Zane's taller, but the question is not asking who's taller. It's asking who's taller relative to the population that they're from. So what we're going to look at first is we're going to look at Jordan. She's going to be over here at relative to the girls. So we're going to look at her mean. Those girls have a 52.5 inch mean and a standard deviation of 2.5. So since Jordan was 55, 55 minus 52.5, and then divide that by 2.5 will get you your Z-score for Jordan. Always use Z-scores when you're comparing. You'll get 1. So Jordan is 1 standard deviation above the mean. Let's look at Zane. Now Zane, while his height is 58 inches tall, the average is 56.5 with a standard deviation of 3. Let's plug those into the Z-score formula. You're going to get 1.5 divided by 3, which is 0.5. Zane, relative to the boys, is actually shorter than Jordan is relative to the girls. He's only half a standard deviation above. So we're going to say Jordan is taller relative to her sex and age group than Zane for the Z-scores. Here's a check your understanding. The U.S. House of Representatives has 435 voting members. The number of representatives that each state has is based on its population when the national census is taken every 10 years. A dot plot of the number of representatives from each of the 50 states in 2024 is shown along with summary statistics. North Carolina has 14 representatives. Calculate and interpret the percentile for North Carolina. Pause the video and see if you can try this. All right, here we go in 3, 2, 1. So with North Carolina, 14 representatives, there's going to be 43 points at or below 14. You can do the math and count those if you want. So the percentile is going to be 43 divided by 50. So there are 50 states. That's going to be 0.86, which is the 86th percentile. Let's do the interpretation. Remember, percentile is the number at or below that. So in this case here, the number of representatives NC has is at or above 86% of the states. Is at or above 86% of the states. Look at South Carolina. They're in the 52nd percentile. Which one of those points is the 52nd percentile? Well, remember, 52nd percentile is going to be somewhere in the middle, so not too far from there. How many representatives did South Carolina have? So remember, with this one, you want to work backwards. So let's start by solving that for x. What that's going to do is give you the position. Then you can use that position to figure out what point that actually is from the data. So multiply by 50. You'll get 26. So the 26th position. So I would count from one end. So let's see, this is going to be 1, 2, 3, 4, 5, 6. That's 7. So 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So it should be this number right there. Let's see how close I am. Yes. So the 26th position is going to occur at 6 on the graph. So that's 5, 6. So the number of representatives South Carolina has is 6. Part C, calculate the standardized z-score for South Carolina. Interpret the value. Now that we know that their value is 6, we can calculate the z-score. Here we go, 3, 2, 1. So value minus mean divided by standard deviation. The value is 6. The mean is 8.7. The standard deviation is 9.69. So plug those into the formula. You get negative 0.28. South Carolina's a little bit below average. In fact, it's 0.28 standard deviations below the mean for the number of representatives they have. And part D. North Carolina has 100 counties. In which distribution, number of representatives or number of counties, is North Carolina's relative position more unusual? Unusual in this case would be maybe a higher or lower z-score, but a z-score that's further away from 0. So I'll just say further away from 0. That would be a more unusual z-score. Let's remind what the number of representatives values North Carolina had. They had 14 from Part A. So we want to get the z-score for both the number of representatives and the number of counties from the data up here. Let's start with the counties. It's going to be 100 minus 62.82 divided by 46.421. You'll get 0.80. Now let's do the z-score for representatives. We'll do 14 minus 8.7 divided by 9.69. And that's going to be 0.55. Now, which one of those is further away from 0? Well, it's going to be the 0.80. That's the more unusual one. So the county, in other words, North Carolina has more counties on average compared to the number of counties that a state has than representatives, which means the counties in North Carolina tend to be on the smaller side. The last part of this video is going to be talking about cumulative relative frequency. So you've seen histograms before with all the percentages, relative frequencies, and we've talked about cumulative frequency. So where we're just adding the numbers up, and that's going to give you this number here, and then you could add to that 28.26 to get this number, and so on until you get to 100%. Cumulative frequencies are helpful to help determine where a percentile is. So for instance, the 95th percentile would be somewhere around between 65 and 70 for that age. In this case here, we're talking about the age of US presidents that when they took office. The first 46 presidents and their ages when they took office. And you can see that distribution is slightly skewed to the right, peaked at around between 50 and 55. So let's answer a couple questions related to that. Before we do that, let's talk about this graph. This is a cumulative relative frequency graph. What it does is it shows you starting at 40. In this case, we start at 40, so that's going to be at 0%. And between 40 and 45, that percentage rose that relative frequency to 4.35%. So you look on the graph here, and this dot roughly translates to about 4.35%. And then the next bar, that's going to add another 15.22%. So we're looking at around 20%. In fact, it's 19.57. And if you add all those numbers together, eventually you're going to get to 100% all the way here at that last interval, which is over here between 75 and 80. Here's the question. Part A. Was Barack Obama, who first took office at age 47 years, 169 days, which is about 47 and a half years, unusually young? Explain your answer. Now, it is on the younger side, but was it unusual? In other words, was it like less than 5% unusual? That's kind of where we're going for with that. So let's look at the percentile for Barack Obama. What we're going to do is we're going to look at 47 and a half, roughly about here. And we're going to move it over to the percentage side. So we got the age. Percentile looks like it's going to be, well, halfway between 0 and 20. So I'd say it's around the 10th percentile. So it's young, but is it unusually young? And I would say no. While it's on the lower side, it's not unusually young because it's not, you know, below 5% of the data. Part B, estimate the 65th percentile of this distribution. So to estimate the percentile, we'll look at the cumulative relative frequencies. 70 is about here, so the 65th would be somewhere around there. If we just take that and extend it over here, then we can move down and roughly estimate where that age is approximately. Here's a better drawing. And it's going to be about, I would say 58 years, maybe 57. Estimate the IQR. So the IQR comes from Q3 and Q1, which is the 25th and 75th percentile. And we can get those from the graph as well. So we want to estimate where those are on the straight down to the age, and it looks like it's going to be about 60 and 51, which means the IQR will be whatever those subtract to, which is about 19 years. Lastly, let's do a check your understanding. So we have another cumulative relative frequency graph. It summarizes the data of the length of phone calls made from the office at Gabelot High School last month. About what percentage of calls lasted less than or equal to 30 minutes? About what percentage of calls lasted more than 30 minutes? And then finally, we want to estimate Q1, Q3, and the IQR. So pause the video, try this one on your own, and then we'll go over the questions. All right, hopefully you got a chance to work this out. We're going to go over this in 3, 2, 1. So part A, the percentage of calls that lasted less than or equal to 30 minutes, is roughly going to be about 67%. You could make an argument a little bit above or below if you want, but that's where I got for the graph. Part B then is talking about what percentage of calls lasted more than 30 minutes. Well, more than 30 minutes would just be what's left over. So it's going to be the 100% minus 67%, or 1 minus 0.67. So we'd say 33%. But then the Q1 and Q3 and IQR can come from the 25th and 75th percentile. So we'll get those two numbers here. And again, just estimating those, it looks like I get about 32 for Q3 and 13 maybe for Q1. We'll subtract those to get 19. So the IQR of this distribution is once again 19. And finally, to wrap up this video, we're going to be talking about what happens when you transform data. So when you have a distribution of data, remember the test scores from before. If you simply just add numbers to those Say your teacher wanted to bump up 5 points since the highest number, since the grades weren't terribly great, maybe we want to boost the percentage up a little bit. So add 5 points to each. What does that do to the spread? Well, effectively nothing. The spread is going to be the same, but everything else, the shape will be the same, but the center is going to be moved up 5. So if you look at the mean, you can see that center was just added 5 to those. And we've done this with random variables before, so this shouldn't be new to you. The shape will be the same. The center is going to be about 5 units higher, and then the variability will be the same. It's going to have the same standard deviation. So you can look at those two standard deviations here and see those are exactly the same. Now, what happens if I decide I want to make it out of 100? So in this case here, instead of out of 50, 100, I'd have to multiply by 2. Well, does that change the shape? No, still going to be the same shape. The center is going to be bigger. It's going to actually be doubled as well. So if you look at the mean, look at those two numbers. That 80 is definitely twice as much as 40. And that standard deviation is also going to get doubled. So when you multiply, you also multiply the standard deviations, but you don't add or subtract. And lastly, what happens when I do a z-score? So with z-scores, if I were to convert all my grades to a z-score, look at my original. And remember, z-score is value minus mean divided by standard deviation. Now, is that going to change the shape? Well, over here, it looks like the shape's really kind of smushed together, so it's kind of hard to tell. But if we rescale that so that my numbers are counting by less, it's actually the same distribution. So the shape's going to be the same. The center obviously is going to be much different. In fact, it's going to be 0. Look at the mean over here. That mean is 0. Now, how do we get the 0? Well, it's just the mean, the value minus the mean. So literally the value is the mean minus the mean, which is 0, divided by anything is 0. So the center for all z-scores is going to be 0. The variability looks like it's going to be 1. Now, where does that 1 come from? Well, remember that with standard deviations, we don't subtract the mean. So if I plug in my 8.771 as my value and I subtract the mean, I'm not really subtracting the mean. So really, I'm just dividing the standard deviation by itself. That's going to always give me 1. So the mean will always be 0, and the center will always, or the standard deviation will always be 1 in a z-score standardized distribution. So let's summarize that real quick. For adding or subtracting, the shape will always be the same. We add or subtract to the means. We do not do anything with the variability. It's going to be the same. So if it's standard deviation, IQR range, the variability would be the same. Don't mess with that. When I multiply or divide, the shape will still stay the same. We multiply or divide the center, and we multiply or divide standard deviation. So that does change. And then z-score, the shape will stay the same again. For the center, we are going to always have 0. The mean will be 0 because you're subtracting the mean from the mean. And then the standard deviation will always be 1 because you're dividing the standard deviation by itself. You're not subtracting anything from it. So 0 and 1 will always be the mean and standard deviation of a z-score distribution. Knowing that, let's look at this last example. During winter months, temperatures at the Starnes family Colorado cabin can stay well below freezing, 32 degrees Fahrenheit or 0 degrees Celsius, for weeks at a time. To prevent the pipes from freezing, Mrs. Starnes sets the thermostat at 50 degrees Fahrenheit. She also buys a digital thermometer that records the indoor temperature each night at midnight. Unfortunately, the thermometer is programmed to measure the temperature in degrees Celsius. Well, here are the dot plots and numerical summaries of the midnight temperature readings for a 30-day period. So we have the dot plot. Looks like it's a little bit skewed to the right. All your summary statistics, your mean and standard deviation are going to be the most important here. And here's a formula we can use. Suppose that Mrs. Starnes converts all the temperature readings from degrees Celsius to Fahrenheit by using this formula, where the Fahrenheit degrees is 9/5 times the Celsius degrees plus 32. Part A, what shape would the distribution of the indoor temperature reading in degrees Fahrenheit have? Well, the shape's not going to change, so it's going to be exactly the same, about skewed to the right a little bit, single peaked. Part B, find the mean indoor temperature reading for degrees Fahrenheit. Does the thermostat seem accurate? Well, the mean we add and subtract, we multiply and divide, we do all the operations. So we're really just plugging in the mean of our Celsius. So our mean is 8.43. We're going to plug that in for the degrees Celsius. And we're going to add 32. In your calculator, you get 47.174. Now let's look at the thermostat setting. Mrs. Darden set a thermostat at 50 degrees Fahrenheit. So it's not quite accurate because it's a little bit below what the thermostat set at. So does that seem accurate? I would say, nah, it's a little bit off. Part C, calculate the standard deviation of the indoor temperature readings in degrees Fahrenheit. Well, with standard deviation, remember, we don't add or subtract, so that 32 will not get used. In fact, just ignore that when you're working with spreads. Just take your measure of spread, in this case, the standard deviation, and multiply it by that number that's there. You'll get 4.06. Part D, or that's it. So you try to check your understanding. Here's the readout. Pause the video if you want to try it on your own. And I'm going to go over it in 3, 2, 1. Knoebels Amusement Park in Ellisburg, Pennsylvania has earned acclaim for being an affordable, family-friendly entertainment venue. Knoebels does not charge for general admission or parking, but it does charge customers for each ride they take. How much do the rides cost at Knoebels? The figure at the right shows a dot plot for the cost of each of the 22 rides in a recent year, along with summary statistics. So there's your dot plot, there's your mean, there's your standard deviation. This is in dollars. Part A, suppose you convert the cost of the rides from dollars to cents. In this case, we're going from 1 to 100. Looks like we're going to have to multiply. Describe the shape, mean, and standard deviation of the distribution of ride cost in cents. Well, that shape ain't going to change, so it's going to be skewed to the right, single peaked. The mean will be 1.705 times 100, which is 170.5 cents. And the standard deviation will also be multiplied by 100 since we're multiplying. So you'll get 44.7 cents. Does that sound good? All right, let's look at part B. Again, try this one on your own. Okay, I'm going to go over it in 3, 2, 1, and here we go. Managers at Knoebels Amusement Park decide to increase the cost of each ride by 25 cents. How would the shape, mean, and standard deviation of the distribution in part A be affected? Explain your answers. Well, the shape's not going to change. It's going to be skewed right, single peaked. The mean, since we do add or subtract, we are going to add that 25 on to that 170.5. So you'll get 195.5 cents. And then with standard deviation, remember, we don't add. So that 25 will not get added. You'll be stuck at 44.7 cents. The spread has not changed. Part C. Suppose you want to convert the increased cost from part B to z-scores. What would the shape, mean, and standard deviation be of the distribution? Well, with z-scores, the shape's going to be the same as before. The mean will be 0. The standard deviation will be 1. Those are always going to be truths for z-score distributions. And that concludes it. The next video will be about an introduction to normal distributions. Thank you for watching, guys.